Hello, and welcome to this week's Quantum Programming Book Club. We've got our usual suspects here, and here's our book. We're almost done. We got 2 chapters, 12 and 13. So I'm going to be leading the discussion this week, and we're going to be diving into Shor's algorithm. So hopefully, if I'm doing my job leading you guys that are here and also listening after I post the recording, we'll get 2 things out of this session. The first thing is an increased understanding of Shor's algorithm. But the second thing is a little window into how I address learning technical information. Because what I found in this chapter is, although I had been exposed to Shor's algorithm before and I was continuing to learn it, I really wasn't satisfied with the amount of information for the level I was at. And so what I did to prepare is I used a technique that I use when I'm studying just on my own. I thought I would just share with the group. And basically it's a way of sort of mapping or capturing. So, hey, Nuri. So I'm going to go ahead and share my screen, and I'll just show you. So can you guys all see that okay?
Yeah.
Okay, so what it is, it's a tool called Mind Map. It's a mind mapping tool. And you can use a spreadsheet or a notepad or whatever, but it's just a tool that I use when I'm studying really anything. And I'm taking the materials that I have, and then I'm noting down where there's gaps in what the materials are providing to me, and then I'm going to go out and research. And so what I'm going to present today is a combination of what's available in the book, and I'll just expand this out. So QC engine, right? And of course, that's going to be the book and code. But I always like to begin with the end in mind. So although that I found the book, the text to be useful and the diagrams to be useful, for me, the code samples, and there are 4 of them that work. Really, one was useful in the QC engine environment, and it was really challenging to me because I was like, I want some working code so I can go further with this, or some code that I can understand. And so I did a number of techniques with the code itself, and then as you can see here, I went beyond the book to try to find some other information. So that's kind of the frame. So this is the map to kind of guide me. Also, I have this goal in life to show as little PowerPoint as possible. So I was going to make a PowerPoint. I said, no, stop. So the first thing that I'm going to do here is get into the book. And the book starts out, and it tells us what Shor's algorithm is. So Shor's algorithm is an algorithm that allows you to find factors of a number. And it's from person Peter Shor, and it can be sped up with taking part of it and making it into quantum. So a couple things about this that are interesting. One, this is an example, and an example that really is kind of a reference example. It's almost like a hello world for quantum computing. Almost every quantum language library hardware will implement Shor's. So it's, kind of important to get into it as much as you can. And 2, it demonstrates this process of when you implement an algorithm, part of it will be run classically and part of it will be run on a QPU. And so, in terms of pure quantum programming, I don't really see any of that out in the wild anywhere. Everything is done this way. So it gives us an example we can get our hands around in terms of figuring out how we're going to separate out the compute. Then the book goes into, why factoring is important, why fast factoring, and one application of that is in public key cryptography, because that depends on the ability to factor large numbers. And so this has been kind of a hype thing around quantum for a long time, like when quantum computing is real, it will break all cryptography. Well, as we will see in this chapter, it is for this algorithm, it's still kind of in its infancy because of where quantum hardware is at. We're not factoring big numbers here. We're factoring 15 and 35 and 125. So as an example. So then the book goes on, and then it takes what I call a leap of faith. And so it gives an example using the QC engine, showing how to use QC engine to simulate using a QPU for the portion of the algorithm that can be sped up. The challenge I have with this is it shows kind of not enough in the book. And then if you go over to the actual implementation, just let me move here. The circles are useless at this point. They don't really do anything. And if you look at the implementation in the orchestration, it's, to me, unparsable, even with the number 35. So that doesn't really help me at all. And the code is long. It's 200, almost 300 lines of code. So, okay, it worked. It worked in this amount of time, but why? What did it do? How is it working? So it's interesting that, the way the author started was with putting a complete implementation. In my studies and looking for different ways that this can be implemented, one of the areas that I looked at is different languages. And so I looked at Python. And so one of the areas that I looked at was IBM's Qiskit. And IBM's Qiskit, you might remember from other weeks, has a series of utility libraries. And in fact, they actually have a library that is called Shor. And so in their series, they take the same approach as the authors do, which is like, here is what it does. You factor some numbers, there's a portion that is quantum, there's a portion that is classical. And the interesting thing about the IBM version is their version shows the overhead to run it, which to me is very interesting. And so I decided I would test that, because the code in 12.1 just wasn't like, I was like, okay, so what? This isn't moving me along. So what I did is I took a look at their library. And what I liked about this, and all the code that I found here, I put up in the GitHub repo, so you can try this out too. So I'm running it in the IBM Quantum Lab. And you can see in the center section here, they really wrote a library for this. In line 4, you just create an instance of Shor and you associate it to a runtime, which is their simulator on IBM. And literally you pass it a number and then you just parse the result. So this is the true black box. And to me, if you were going to just show, okay, this is how you use it, rather than give me 200 lines of code, I'd rather have 2 lines of code. So it was something that I did in my studies, and I just thought it was for me, it worked better in terms of opening. Also,
And Lynn, so in your studies, did you find that it's common in pretty much every environment to have a Shor library kind of packaged and available?
Yes, I did. And that's another reason that I wanted to show that, right? So there's like the full implementation, or there's the library. And so like a really common starting point from different, quantum implementations is run Shor, right? So this is the way I'd like to run it. And then you can see down here, they put in some sample code showing you the number of qubits that are used. The other thing that I want to call your attention to is on line 3, where you're working with the quantum instance and you assign it to the simulator. The shots means the number of times you run it. So it seems to be standard in simulators that you always run 1,000 times. I don't know where that comes from, but that's just really interesting to me, because that's not in the book either. The book sort of mentions it and says you can run it one time and get one result and another time to get another. But outside of the book, every other implementation tends to run it with 1,000 shots, and then they'll plot the results to show you what is the most likely. So to me, that was like a better starting point. So, okay, great. That was the starting point. So now let's go back and go on. And so now the book has an explanation, and the explanation is, okay, we're going to assert without proof a useful fact from number theory. And they do give a reference. It's possible to solve the problem of finding prime factors P and Q of a number, some number, if we're able to solve the seemingly unrelated problem of finding the repeat period of the function a to the x mod n as an integer variable x is varied. Okay, this was really tough for me because basically they're just saying, we're not going to show you the math. Just this is how it works. And what happens for me with this is I can read it and then I don't remember it because it's a random fact and I don't have a reason to remember it. To make it a little bit more challenging, they go on to say, if the idea of finding the repeat period of a x mod n sounds obscure, fear not. All it means is you change the value of x. Eventually, the sequence of numbers repeats itself. And then to keep things simple, we'll choose 2 as our coprime. They don't say why, they just say they are. And then they show something that looks familiar from earlier chapters, which is, finding the period of a function by observing in using a QFT. I mean, that's kind of how we've done previously. And then they go on to tell us a little bit about kind of why this would work. But again, they're skipping over a lot of math. Once you know the period, so like 4 here, right, repeats every 4th value or every 12th value, 12 here, then one of n's prime factors might be given by the GCD of the number with a, the p over 2 plus 1, and the other might be given by the same thing, minus 1. And again, this might, I think, is sort of like there's a lot of assumed knowledge in the book. That's why I showed you the Qiskit where they run it 1,000 times, because again, it's probabilistic computing. And then they say the GCD is a function that returns the greatest common divisor of 2 arguments. The well-known Euclidean algorithm can quickly work out GCD. Well, again, I have a lot of gaps in my math knowledge. So I was like, it might be well known to you people, but I'm not really sure what the Euclidean algorithm does. So what I then wanted to do is jump off and see what I could find there. And so I started jumping off a little bit. And so I started looking at external references. So I wanted to see the Euclidean algorithm. So I was like, okay, is this going to help me? No, because I went to Wikipedia. So the only thing that helped me with this was this visualization of subtraction-based iteration. And again, this might seem like ridiculously, childishly simple, but I could kind of like get an intuition from watching this animation, because as I tried to read this article, it didn't help me. So my point here is when I'm trying to decompose complexity, I'm really going to look for visualizations. Another thing I probably will do is I'll probably try to find some Khan Academy video or something, or 3 Blue 1 Brown on Euclidean algorithms, so that I can get an intuition for it. So you can see here's all the math, which again, if you have more of a math background, you might be higher on the learning ladder and maybe you can make sense of it. But I was like, this is challenging to me. So, okay. Then the authors say, well, you might not even need a QPU, which actually by this point I was getting a little irritated because there was all this assumed knowledge. And then it was like, and you might not even need a QPU. And I'm like, stop it. So we've reduced the problem of prime factoring to finding the periodicity P of a to the x mod n. So you could do it with a conventional CPU. All we need to do is repeatedly evaluate a to the x mod n for the increasing values of x, counting how many times we tried and keeping track of the returns. And it says, okay, if we're either using this brute force function then if we get the same value back, we must have gone through one full repeat mode. Although not immediately obvious, a mathematical property of A x mod n is I can only assume any given value once within a period. And so I'm like, okay, we have a code sample here. Great. So let me go and look at this code sample. So I went ahead to run it. And of course, because it's classical, there's no program circuit. The circle notation does nothing and it works. But I'm like, okay, what did it do? So this one had 123 lines of code. And so it's like, okay, it's classical. I don't have any tools here. And so if it's classical, if I'm trying to understand some code, I want some tools that can help me. So my next thing that I did in my exploration was to jump off of this interface and to say, all right, I'm going to take this code and I'm going to put it in some tools that I can understand. And so what I did was I put it into VS Code. And the first thing that I did is I tried to refactor so that I could have kind of a readable progression going through. So when I started off, because the code wasn't written this way originally, the first section here was just basically setting the number, setting the precision, the coprime, and then here's the, basically abstraction, if you will. It runs Shor's algorithm. And then it basically just checks to see if you have a result or not. Because I'm in Visual Studio, I don't have a QC object. So I just changed that to a console log so I can actually run it in Visual Studio. So this then implements Shor's algorithm. So what is that? So Shor's algorithm has three parts. So it has a repeat period, it has factors, and then you basically are going to check and see if you have the correct result. So in line 18, this repeat period with no QPU, so this is our classical implementation, takes our input number, takes our precision bits and our coprime, which are still kind of magic numbers. And the book says it doesn't scale, but this is kind of the way that it works. And then we're going to get the candidates for our number from the repeat period and the coprime. And then we're going to check for validity, basically. So what does the repeat period do? So the repeat period loops through, does some math, and is finding the period, if you will. What does the factor candidates do? Again, there was a QC print statement here, so I changed it to a console log. And this is, again, using some math. Well, I'm starting to lose it in the math here. I'll just for transparency, I'll just show you here the greatest common denominator and then getting the valid factors. So I can, of course, run this by just going like opening in the integrated terminal. And this is just node. So, but that really doesn't give me access to my tools. So the point here is to be able to, one of the things that I like to do is to debug into things. So I'll just put some random point here. I can set a debug point and then I can run with a debugger, because I don't know about you guys, but when I'm having a hard time understanding all the progression of the loops, I literally, maybe I just have a slow brain. I like to step into them and like see the loop progression, see the code working. Is this something, I'll just kind of pause here. Is this something that you guys think might be useful in understanding this code, or is it more intuitive to you?
I stared at this particular function for a very long time because I'm trying to match it up with kind of the math and the description that's shown in the book. And, again, what's in the book is really light math. So when I was looking at this code, I was looking for, I'm not exactly sure what I was looking for, but I'm like, this doesn't seem like it has enough variables. And then I figured out that it's trying to get back to the value of 1. So it's basically looking to see how far values of 1 are for this, AX mod n function. And so once I figured out that it's not just trying to find an arbitrary repeat, it's actually, okay, I want to find out when one repeats itself. Then it was easier for my brain to accept, but it's non-obvious when you just kind of look at this the first time.
Yeah, and again, I don't program as much as the three of you do, so I am the weakest programmer of the bunch. So to be able to run code in my head is something that I try not to do. I would much rather use a debugger and go, kind of like follow the progression through. So, again, I'm not going to take like a super long time, but I'm just going to say, as I continue to learn, I'm going to find this useful. And I have already that I can pull this into Visual Studio and use my tools.
Yeah, I'm agreeing with you. It's definitely useful.
Yeah. So
I'm totally on with using tools of the trade. That's the right thing. I love it that you're using VS Code. It drove me nuts to read this JavaScript before, or their JavaScripts. I don't know who of the authors, just because they're not writing. They're probably writing MATLAB in JavaScript. I don't know that this is really originated in JavaScript, because they're using isms and things from C and C++, and they're using numbers as Booleans here and there, not in this particular one. And then just when you started saying, I like to refactor things, I don't like using mind maps because it doesn't help me. It's just another label. But when you jump into refactoring and you rename functions to say, oh, they're doing marklar, I'll call it do marklar, and pulling out things into functions and realizing, like this whole business, the one you expanded here with the iter being incremented, and then it's not used in the formula. The function you just expanded, the iter, the outer loop, the variable there is not really used in the formula or calculation. That's odd. That's just not very explainable. So my way of dealing with this whole chapter was to say, there exists a black box where there's a Shor algorithm. Okay, what is it trying to do? Oh, it's relying on frequency distribution. By the way, frequency distribution is difficult and of order unknown, but with a QFT, we can produce superpositioned number of probabilities that it is the right answer, read out the frequency, and then get that frequency from there. So that's my mental model of what's going to be there. And being that the book is how do we program things and not how do we do all math and understand all math required, I'm okay stopping there. And I think that I encountered similar, maybe not at the same point, just brain blocks that I couldn't read past that and say, I understand that. I could read past that by wrapping it in a black box, giving it a label and saying, okay, he's doing some magic here. Let's move on. Because for another application, you'll do another bit of magic. So how much do I need to understand the underlying math?
for sure. So anyway, so then they go on to say, okay, so it works without a QPU. So why are we even talking about this? And again, I always like my performance charts here. So I got to give the authors some props that they put in a performance chart, and they talked about estimated costs to run as you scale, which is like the whole reason, obviously, to do this. And it reminds us of why we're taking the time and trouble to try to learn these patterns, because that's where you would potentially get your quantum speed up. And I'm going to emphasize this because this is something that I learned again, I guess, in reading this chapter. I really thought the state of the ecosystem was further along, and it's still so early. It's still so theoretical, and it's machines that have enough QPUs to actually be significant here are really, really in the hands of the few. It's mostly fintech. It's not in general use at all, but it will come. Okay, so now it says, all right, let's get into the QPU because we need it for scale. So now I kind of like the diagrams in here, to Nuri's point of the intuition. Again, it's a common theme with me over and over and over, diagrams. So again, this relates to the chapter on QFT. And so we can kind of get an idea of what we're doing. And of course, they're showing a DFT, but it's going to be implemented as a QFT on a QPU. And then we're trying to get signal processing, basically. And then again, it's kind of just showing us like this factoring result is this DFT result, which they're not saying we're going to get as a QFT. Well, they're kind of starting to say it here. We're going to get this as a QFT operation. So they go on. And so now they talk about factoring the number 15. And if you remember, the first example they gave was 35. And that was the one that was just like, look what it can do. Now, when they give 15, it becomes a little bit more usable on their tools. So when they give 15, the result that you get is either we didn't find anything or success. And again, I kind of covered that earlier in terms of the probabilistic nature of this. But you can see in the example here that here's our friend, the QFT. So one thing that I did as well in the sample code is you can see here, there's some warnings and stuff. And this has to do with JavaScript type coercion. And so I fixed all these warnings and information when I refactored. Because one of the things that I did after I refactored 12.2 is I refactored 12.1 and 12.3 to match in terms of naming, because the names were not consistent. And there were like comments interspersed, and it just was really hard to parse. But in here, just to look at this tool while we're here, the first section is the init, which we're familiar with, and then we go into a superposition, so that's not really new. Then we do something, and then we do a QFT. So this something is kind of the part that's a little bit mysterious. Now, just to make it a little bit more convoluted, even though they didn't need to, they created a setup speed function. And I think this is because they're encouraging you to use larger numbers for factoring, which they've told you will take up to 15 seconds or longer. And then again, lots of kind of confusing comments. So what I took out of this tool was, okay, we go into superposition, we do something, and then we QFT. And then the code here allows us to take the results of the QFT, and sometimes it results in finding appropriate factors for us. But because I had done the work in Visual Studio, I really just didn't spend too much time in here. And I went back into Visual Studio. And for both 12.1 and 12.3, which are basically the same thing, what I did is I took the refactoring that I did in 12.2 and I applied that to 12.1 and 12.3 so that I could compare. So for example, we have Shor Classical and Shor Quantum. So I made everything align so that I could compare, okay, what is different? So, you know, obviously here, there's really nothing at this point that's going to be different. And then in the Shor algorithm, the repeat period, no QPU, and I actually should open 12.3 because that's the one that I did more fully. I was really into refactoring, can you tell? Was having my fun with refactoring. Yeah, here we go. And notice how this is just another thing that I do to reduce complexity. I'll really try to focus my attention on the particular method that we're looking at, the particular function. It's just a habit. So I don't know if that's helpful to you guys or not, but you can see like, okay, set repeat period, Shor QPU, set factor candidates, Shor logic, check results. And then inside of here, this is the classical, this is the Shor. And then to make it a little bit trickier, they have this with modulo or without modulo, which is really the implementation. And again, I aligned all the child methods. So these are helper methods to set up speed, the read unsigned. So, and I took out all the comments. So Shor without modulo is basically the quantum equivalent of the repeat period. And again, I can't say that I am an expert and I can explain this to the nth degree, but cleaning the code allows me to compare more easily. What I'm trying to do there is reduce the cognitive overhead of jumping around in the different methods and stuff like that, so that I could just focus on the areas of the code that were truly different. And like I said, I can't say that I'm done with this effort, but because it took a lot of time to do it, but it was helping me. So I don't know if that will help you guys, but just wanted to share that with you. So is that useful? I'll just put that out there while I'm getting ready for the next part. Helpful, useful?
Yeah, I think
Yes.
refactoring and cleaning up is just always.
Yep. Okay, so, all right, so that basically is the example that we looked at where we're looking at on 15 that has just the couple of preparatory steps. I do like the circle diagrams. This is like the last week that we had. The circle diagrams that are in the book are actually good. So, which do not show up in the actual programming interface. So to kind of go back to this example, we, are starting off and we're setting up our init, which that's not new news there in our circle diagram. Then we're putting everything into superposition, which again, that should be pretty familiar. And then we're doing the conditional multiply by 2. And so what this is doing is based on our coprime, which again, it's a mystery number to me. I'm not really sure, other than it's simpler, why you choose a different coprime. It's just, we have 2, it's a simple one. It impacts the algorithm. Maybe it's a little bit of a hint here. Multiplication by 2 or any power of 2 can be achieved on any binary register with a bit shift. So it's simpler bit shift, I guess. So we're using row left on QC Engine, which is utility method. And yeah, I'm just really not, again, it's just too many different things. So they're saying it'd just be harder for us to explain how it works, but I'm not buying that. I'm like, does it run more efficiently or something? I'm just not really sure. So
Well,
here's
the impression I got was that, well, they say 2's easy to use because of the multiply thing, particularly in the quantum world, right? We've already seen how kind of classical math is difficult in the quantum world.
Right.
But I think it also mentions somewhere that 2 doesn't work as a coprime for certain values. And it doesn't, I don't think it really describes what those values are.
Yep.
Kind of the feeling that I have, whether it's right or wrong, is that when you're dealing with larger numbers, a larger coprime would be a better choice. But, that's just kind of a feeling that I have.
Yeah. But again, we go off into the land of fuzzy, like,
Yeah.
what coprime and how, anyway, so fine. So we're visualizing this. And again, give props where props are due. So this is a row left. That makes complete sense to me. And, all right. And then we do a conditional multiply by 4. Next highest value, the precision is 1. It implies the binary value of X requires another 2 multiplications of 2 on the work register. We perform a shift of 2 qubits on the conditional value to roll. Now we have a value of a to the X in the work register for whatever value of X is encoded in the first 2 qubits of the precision register. Precision is in a uniform superposition of possible X values to obtain a corresponding superposition of associated X values in work. Okay, after we perform these necessary multiplications, it may seem like we've fallen short, taking no action take care of the mod part of the function. Again, I'm just reading words and going on faith here, because the level of abstraction is not working for me. It's just not. So, but I look at the diagram, that helps. So, okay, fine. Then we have this diagram that I think if I look at it, is that right? Yep. Boop. I always can draw the lines, right?
Yeah.
Yeah, there we go. Then I can get it. Okay. So then we have our pattern. hey, that looks familiar. Thank you, authors. Yes. And they rotated it. Now we have the signal. All right. So, and we have the DFT spike counting trick for finding the signal repeat. It's the QFT, which is the end. So this part makes sense to me. I don't know how you guys are doing on this part, but once we get the signal, I'm not sure how we got it, but once we get the signal, figuring out what it is using the QFT, I feel sort of like comforting and familiar at this point. It's like, okay, I know what we are doing now. So, and then we go and we get the QFT value and we get our spikes.
So
And-
maybe this is something we could talk through. I don't know if Jeremy or Matt have, or you, Lynn, what is the mental model of what happened before we tried to extract these frequencies? Why are we extracting those frequencies? Like these frequencies, to
yeah,
my
because-
understanding, the periodicity tells you that it's an integer. The fact
Yes.
that there is a frequency
Yes.
tells
yes,
you that it's an equal divisor.
Yes.
Okay, so all of these machinations were math, I wouldn't call it math, an algorithm to coax a frequency out of all of this.
Mhm.
And then the
Yeah.
rest is kind of trivial, right? The rest is downhill from there.
Well, that's my
feel
feeling.
good.
But again, I mean, showing my exploration, I went off to another place here. So I went to a blog, and I went to this blog, and I was trying, and it had like a little bit more math, and so I was trying to see if I could get there. So maybe this will be helpful because this is the classical part. And then we go into the quantum part, but he starts right off with tensor products. And I mean, I have done this, but I just haven't done it recently. So I was going to try to work through the math in this particular blog post, but I don't know that I want to do that, live. I kind of want to leave it as a reference for people.
Yeah, and I also worry there was some comment on that Shor's or the implementation is somewhat QPU dependent,
Mhm.
which to me says that we're not dealing with the same algorithm in a way, because we are saying for certain QPUs, certain math or matrix or whatever operations are hardware baked, and for certain they're not. And it might be that they're arriving at these calculations instead of by doing matrix multiplication or dot products and all of that jive by doing something else.
Well,
So-
to your point, again, I always go for simple as possible. So I found this blog post that it was kind of driving me along the route of it. And it was kind of like a minimum viable. And so, he's basically, I can pretty much follow what he's doing here. Suppose we have n equals 21, we randomly choose integer x less than.
Dude, lead with that. This is so much simpler.
Well, that's what I'm saying. That's what I'm saying. Well, this is part of the point of the exploration, right? Okay, and then we want to find the order of 8 mod 21, and then basically this is showing the period. So now we know the order of 8 mod 21 is 2, r equals 2, and now we're going to check if it's odd. And then we go back to step 1 and choose another x. And then he goes on and he's showing the formula here, because remember, this is the formula of whether it's factorable or not. And then he goes and shows just enough math of why this works, which I was like so happy I was crying at this point practically, because after all these hours, right? So this was just enough math for me. It was like, okay, here's the math. This means n or 21 is made up of 2 prime factors that divide. And then he does the little math here. P divides n, Q divides 7. There it is. And there's our result. And so I haven't quite connected this back to the JavaScript yet, but I was able to follow this. And so again, I put this on my GitHub. I put a link to this. And then he goes into Shor's algorithm and he says, it's inefficient. And then he literally says, in an actual Shor's algorithm, quantum Fourier transform will be implemented here. And then his purely classical, because the guy's obviously a good programmer, is this is a much better algorithm. And look at that. This is something we can really get our hands around or heads around. So again, I know I'm throwing a lot of information out that you guys didn't take the time that I did, but to me, this is a subject area that I have to put more time than just an hour into. And I liked this implementation because it was just enough math for me. So again, I have that linked. So I don't know, am I being too random? Are you guys like, she's going all over the place?
No, this is great.
This
Okay.
great. There's one mathematical bug that I got now that I didn't get from reading chapter alone, is that GCD is just GCD, but the problem that he's trying to do is prime factors.
Yes.
So you need to also prove that these are the only factors,
Yes.
which is a slightly different or completely
Yes, it
different problem.
is. Yes, it is. There's this assumed knowledge that's in there that is not, there's just all, yes, exactly. Okay, so then read the result. Okay, we're all happy. Okay, we could have received this value. Okay, so now we have this 12.4 code sample, which is, as we noted earlier, given our knowledge QFT spikes are evenly distributed, we can determine what periods are consistent with our read value using conventional digital logic. The estimate number of spikes function explicitly shows the logic for doing this. In some cases, this function may return more than one candidate. Okay, book club friends, why do we have to have this function? Does anybody have an idea of why they're showing us this? I was like, okay, great. It can return the number of spikes. Okay, why? Why do we care?
Well, the number of spikes is the period that we're looking for, right? So from those previous charts,
Yeah.
you know, it was either 4 or 12.
Okay.
In the little spike charts.
Okay.
I think again, kind of the impression I got is that if you're not running this 1,000 times, then the read value that you'll get out of this is going to be a 0, 4, 8, or 12.
Okay.
And so based on getting one of those values, you can chuck it at this function to figure out the likely number of spikes. That's how I interpreted this. I think it would be more, I think if we were to go with the, you know, we're going to do 1,000 shots, then it would be more clear. Okay, well, when we do 1,000 shots, we have 4 values come out. So those are our spikes. You know, does that make sense?
Okay.
I think this is a way of getting around running this 1,000 times to figure out where our spikes are.
That was my guess.
Yeah, that's the impression that I got from this.
But it seems unusual because when I look at any of the other implementations, they always run them 1,000 times and they never talk about this kind of thing.
Well, this definitely, I mean, they present this as this is a simplified version.
Yeah, for sure.
So, and that was actually helpful to me because knowing that something that's more, I don't know if flexible is the right word, but can handle more different kinds of input values. This, again, I didn't go through the code line by line. I was more looking at how the book presented the steps. But that did give me an understanding of, okay, well, here's why the period is important. And then, you know, I actually did the little GCD thing by hand on my little,
awesome,
you know, multiplying out the powers to see how that came out. So, you know, as far as what I got out of this is it gave me a good idea of how we could use the DFT, QFT stuff that we learned in previous chapter so that we didn't have to do this brute force to figure out what's the period of this AX mod n function that we're trying to get that value for. So then once we have that, we can throw it at the classical. So I feel like I'm talking in circles.
No,
but kind of the simplified version helped me understand, here's the big concepts around Shor's and the quantum part and how the quantum part relates to the period things that we've looked at in previous chapters. And then I'm just kind of taking all of the AX mod N and the GCD with the, A power divided by 2 plus 1 minus 1 things. I'm taking all that on faith. And, based on the numbers that they're showing and me working out these simple math problems, I understood how it was going there, but also realizing that, yeah, I can figure out with trial and error a GCD of 35 and 65, which is one of the values I got, and 35 and 63. If those numbers were a lot bigger, then I wouldn't be able to figure that out in my head, and I would need to go to that Euclidean thing that you were looking at before to find that. So I was taking this more from the intuition standpoint, and the simplified version is helping me understand it. And actually, the reason I asked you about what you found in the other, that it Shor's exists in libraries basically everywhere, is me trying to figure out, is this something that I'm going to have to implement myself? Or is it something that I feel like, okay, well, I have a general idea that when you turn the steering wheel, the car goes in this direction, and I don't really have to worry about all the connections in between. So that's where I am, and I'm kind of comfortable without needing to know all of the details.
And that's interesting because, again, in my little map here, as I was trying to learn more, I would stop at various points, right? And so like for 12.1, I just stopped because the code was too complex, right? So 12.2, I used VS Code, I refactored and used the tools, right? 12.3 was usable. That was 15, right? But I did refactor it as well. And 12.4, I just didn't really understand the point, but I refactored it anyway. So, that was what I got out of this, but I wanted to learn more, right? And so, I looked at this visualization, I looked at that math blog that I showed you, but it was too complicated. So I stopped again. And then I was like, okay, are there other samples? Because, I do know C# and maybe I should look at it that way, because there's Q#, and there was a Q# sample, but unfortunately it actually didn't work through errors. IBM has OpenQSAM. There wasn't really a sample I could find. Plus, I'm not a C++ programmer, and OpenQSAM is more like C++. So I discarded the C stuff. The Python world seemed to be the most friendly world. So I showed you that open source example that I really, really liked, that I'm going to actually spend more time with on that one Python notebook.
Yeah, and that one looks very useful.
Yeah, so I linked that. So then I wanted to look at Circ and Qiskit. So Circ is Google's library, and Qiskit is IBM's library, Python libraries, because I wanted to see like what they might have. So the first thing I did was Circ runs in Jupyter Notebooks, and it runs on Colab. And so I was like, okay, let's see what they might have. And they had a notebook, but to your point, Jeremy, of saying I feel comfortable, I'm just going to use the algorithm. They literally started with the derivation, and it was like mind-bendingly hard. So what I did, because again, I was just trying to challenge myself, is I refactored the notebook because I'm just interested also in the process of refactoring different environments. And so I took their Colab notebook and I refactored the notebook, and I actually did so much changes to it. I made a little presentation. I recorded it. I'll link it. It's 15 minutes long on my process of refactoring a notebook, because it's kind of a separate topic, but you do get into it with these kind of, I guess, call them vanity ways of working with QPUs and GPUs and, all this kind of stuff. So the sort of the TLDR is in the notebook, they had notebook text, they had comments, they had visualizations, and nothing really matched. Plus, and I'll just show you kind of like the end result here. They have the ability to have a table of contents, but they didn't really write it like a book. And so what I did is I redid the table of contents. I program like a writer if I'm successful, I guess, in a way. And so they start with this order finding problem. And I imposed this structure on their notebook, but they compare classical order finding with quantum order finding very similarly. And again, I was just trying as a mental exercise to look at different implementations. Honestly, this didn't really bring me further along. It was an interesting exercise, but it didn't. What did bring me further along is the IBM stuff. And again, I wanted to make sure and share that because that's kind of the area that I'm going next. So they have a textbook, which looks really interesting to me. And they have an interesting implementation that is pretty consumable as well. So again, the problem, period finding. Yes, this is what we've been talking about, right? Let's look at the function, right? Da 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 da, there it is. The solution, use a unary, da 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 da, right? So it reads to me in a way that I think about this problem. Plus, they have this click to expand, which I really, really like in their notebooks, which basically, if you don't want to see the math, you don't have to. So you can like expand and collapse the math so the math doesn't like overwhelm you. So my feeling about where I'm going to go next for learning is I'm going to go deep into the IBM implementation because I think that it is going to be the most useful example. And again, coming back around to where I started, I really like the fact that in their reference library, they talk about the number of qubits for the circuit so that they have this aspect of real world performance and overhead. Because to me, I don't want to spend all my time with these difficult mental concepts if I don't have some sense of where they are based on reality, right? Even if my finding is, oh, you can only factor numbers of like up to thousands or whatever based on the resources I could afford. That is important to me in learning about this because I'm not that much of a nerd that I just want to learn things that are so theoretical. I have a hard stop. So yeah, and I just mapped this out again in my thinking about this because one of the things I really want to call out too, because people ask me a lot, they say, you know, how do you have time to learn things, right? How do you do that? And having your own business and having your own consultancy. I do it because of the word stop. When I am doing this kind of learning and trying to be broad in looking at the different resources, very much like any other aspect of work, I time box my learning. And, you know, the textbook is useful. And so I'm going to continue with that, right? But the example is still a little bit complex at this point. So again, I don't know if this metaphor is useful for you guys, but it's something that I use. And I use because I'm always seems like I'm studying like 3 or 4 out there on the edge things at one time. And so I will kind of have this content repository to organize myself. All right, and to finish up the chapter, because there's the fine print, the hard stuff, because we didn't have the hard stuff yet. So it talks about how they compute the modulus. And it shows you a little bit of math. And then it talks about kind of the overhead to it. They talk about the coprimes other than 2. And they just continue to say that it's a simplification. And that is the chapter. So my feeling with this is I found resources that can take me further. The exercises that I did in refactoring were helpful to me in terms of program flow. And so I've chunked them out so that I can like compare, like, okay, the sections that are different, I can now look at them because I've made them as, put them in as similar containers as is possible. But I still need to continue to work on this because it's not where I want it to be yet. I'm not just going, oh, Shors, yep, okay, got it. The way that I would liken this is when I was learning machine learning, there is a sort of a reference implementation for neural networks. It's called MNIST. You guys may have heard of it. It's the digits, like classifying the digit problem. It took me probably about 6 months to be comfortable with TensorFlow on MNIST. Not every day, but just in my spare time. And I just picked at it. And again, the reason I'm discussing this is because I think it's important to be honest about how much time learning complex concepts takes different people. And everybody has a learning ladder based on your life experience and time and everything, and a level of motivation. So my motivation is big because I want to get to the sort of the understanding level that I have with MNIST, which I'm really comfortable now, and I can use it to evaluate TPUs and TensorFlows and neural networks. And I want to get there with Shors. I've moved forward with this book and other resources, but I have more work to do. And that is what I have to say about this. So,
Yeah, well, thank you, Lynn. That's really cool.
Yes.
yeah, so did I stop sharing?
No, you're still sharing.
Okay, so how do I stop sharing? Stop sharing. All right, well, we're pretty much done anyway. So next week we have talking about machine learning, because this week was not challenging enough. We have quantum machine learning. And to give you a preview, it's going to be a similar approach because I think the authors ran out of time. There is no executable code in chapter 13.
Or
So,
the field's moving so fast,
yeah.
there was no point.
Yeah. So in any case, oh, there we go. So in any case, I'm going to take a similar approach to next week of being a content curator. I've already kind of started it, and I probably will talk about MNIST. So if you're, it's going to be, a good mountain at the top of the book. So I don't know if anybody else has anything to add before I stop the recording.
Nope.
I think the only thing I would add is, yeah, clear at this end of the book, it is a complex book. I am now taking things on faith, getting the mental models down, and I'm considering that a win because it is going to take time to sink in or let my brain, juices digest a bit. Knowing that I'll see something in a month or two going, oh, now I've got something to hang those ideas on. But yeah, I'm still in that space as a developer. I don't mind getting into the nitty-gritty of complex algorithms if I understand pretty thoroughly what the concept is behind the algorithm. If I don't, then the algorithm is a little hard, and I'll do what you did, refactoring and trying to go line by line, pulling out a debugger. Yeah, I think at this point in the book, I'm wanting to grasp the mental picture. I'm not so worried because I know that someday if I have to put something in action, I'm going to be looking for the Shor function in the Python library. Yeah, and my heart, and I think I've struggled with this the whole book, and I've really enjoyed it, but the struggle I have is kind of, again, trying to identify as a developer, what are those problems I'm going to come across that I need that light bulb to go and say, oh, wait, this is a perfect QPU problem, type thing. And as you guys were mentioning, Jeremy, I think you mentioned that this is a simplistic problem. Lynn, you were talking about that function. What do we need this for? Yeah, QC engine isn't meant to run 1,000 iterations and give you an answer. So there are times in other examples we've looked at that we've literally clicked, hitting the button, and we're like, oh, look, you got that other option. Okay, no, I didn't. Oh, look, we got the other value in, where we see that. And I'm thinking that, because it's so expensive, we're talking about concepts that we can't afford to run. So we're trying to tweak them in a way that says, look, here's a small usable example, assuming you use our magic numbers, but we're trying to get the concept across. And so I think we're in that difficult space of being professional developers, trying to learn something that we can't physically do yet, but still get the concept, So that's where I'm at, but I love it. Thanks so much for everything you showed.
Sure, well said.